Okay, ladies and gentlemen, coming to you from my basement. Not a good situation, but it works. I have a short list of perfect squares that we'll be extracting from roots, some perfect cubes we'll extract from roots, and some perfect fourth powers there that we're going to extract from roots. I'm going to give you a second here to do warm-up problem 1, 2, 3 to see if you got them right, and we'll start in a second. Okay, so number one, you got the square root of 40. See that as the square root of 4 times 10 because 4 is a perfect square. That 4 comes out. The square root of 4 is 2 times the square root of 10. There's no perfect squares in 10, so we stop at 2 square roots of 10. We come over here to number 2. This is a cubed root up here, and when I'm cross-referencing my cubed roots, I'm going to look over here. I see 8 is a perfect cube. 24 is 8 times 3, so I can extract that cubed root of 8 out there, and that's going to be 2 times the cubed root of 3. To get all the way down, there's no more cubes in there. Then I come up to the fourth root up here on this one, and I'm always thinking smaller numbers. I'm a small thinker. I got 16, so I'm really looking at that as the fourth root of 16 times, what would that be, 3? Think so, and the fourth root of 16 is 2 times the fourth root of 3 would simplify that. So we're just extracting whatever perfect roots, all of them that we can get out of that number. Big topic for today, rational exponents. That just means exponents that are fractions. And anytime you have an exponent that's a fraction, you actually have a root. And when you look at the root, the number that's underneath the power goes underneath the square root symbol, and what is in the denominator of the fraction goes where I call the saddle. And the m, the numerator, can go one of two places. We can put it underneath, above the a, or we can say, this is my n, my a is here, and I can put it all the way on the outside, so that I can take whatever root this is and then just raise it to that power. Example right here, 7. Now when there's nothing written in the saddle here, when it's bald, that's a 2. So the square root of 7 as a rational exponent is 7 to the 1/2 power. And if I'm looking at 16 to the 3/2 power, okay, the 16 is going to go underneath the root. The denominator here is going to go where I call in the saddle. And I always like to put this numerator on the outside so I can look at this, the square root of 16. Well, I know the square root of 16, well, that's 4. And then I got to cube that 4. And 4 to the 3rd power is, right up here, it's 64. Okay? So I got to erase and reload my board. Back in a minute. On your note sheet there where it says now you got some choices how you're going to evaluate this root. Well, like I said, there's two ways to do it. I can look at this with my square root, put the 4 underneath the root, put the 2 here, and I can corral the 3 to the outside and say the square root of 4, well, that's 2, and I still need to raise that 2 to the 3rd power, and 2 to the 3rd power is 8, so I get there. Or I can do it this way, I think is a little bit more complicated. If I put a 2 here and put my 4 underneath and I put a 3, well, I can look at it like this. I can raise that 4 to the 3rd power first and say, hey, that's the square root of 4 to the 3rd is 64. And then the square root of 64 is 8. I get to the same exact spot. Either way you slice it or dice it. But I like this top one, keeping that root on the outside here. I think it keeps your number smaller and things go a little bit better for you. Next 4 we have here in line on your note sheet, we have simplify the cubed root of 8 raised to the -2 power. Take it in baby steps. The cubed root of 8 is 2 raised to the -2, and I know the cubed root of 8 is 2 over here on my perfect cubes. And remember what negative exponents do. They make you see fractions. That's 1 over 2 squared, and then it makes the exponent positive. And that gives me 1 over 2 squared is 4. So it's just another way to see the cubed root of 8 raised to the -2 power is actually 1/4. What makes this one special, the 6th root of 64? Well, what makes this one special is when I'm looking at the sixth root, if I take 2 times 2 times 2 times 2 times 2 times 2, 6 2's, and multiply 6 times or 2 times itself 6 times, we get 64. The sixth root of 64 is because there's a group of 6 of the same number underneath that root. That's just going to be 2. How does this one compare? The eighth root of 64. Well, when I'm looking at this, I can kind of look at this. This is the eighth root. Now, from above up here, I know I can shorten that up a little bit. I know this is 2 to the 6th power. So if I want to rewrite that with a rational exponent, because there's not enough of them to come out, that's really 2 to the 6 over 8 power. And notice I have a fraction here. Anywhere, anytime you see a fraction, you can reduce that fraction, and that's going to give me 2 to the 3/4 power, which actually is the 4th root of 8, because 2 to the 3rd is 8. And down here I have evaluate 2 over 8 to the negative 3/2 power. That negative exponent means this is 8 to the 2/3 power, which fraction exponents give me roots. The denominator goes in the saddle, numerator goes outside. Cubed root of 8 is 2 squared, gives me 4. Load up a few more problems for you. I'll let you look at that a second. Back up the train here, I wrote a wrong problem. So rather than redo it, this was really, how is this comparable? Grab my right sheet. That's really 8th root of 16, which gives me 8th root. 16 is 2 times 2 times 2 times 2, which is really the 8th root of 2 to the 4th. Then, because there's still not enough 2's to come out, that's really 2 to the 4 over 8 power, and because there's a fraction, I can reduce that. It's really 2 to the 1/2, which is actually the square root of 2. Sorry for writing the wrong problem down. Hopefully that is fixed back up. Hopefully there's not too much glare on my screen and you can read this, but we're almost done. Another method here to evaluate the 4th root of 81, just to bring it back to the olden days, prime factor trees. If I think about this, this is 81 comes from 9 times 9. I bring them all down to prime numbers. 9 comes from 3 times 3. 9 comes from 3 times 3. So that means the 4th root of 81 actually equals the 4th root of 3 to the 4th. And because that root on the outside equals the exponent on the inside, well, it's 4 3's that come out. So actually the 4th root of 81 comes down to 3, just prime factorizing them out. And now these last 4 problems we're going to solve using your knowledge of nth roots. That's just something higher than a square root. And we're going to solve these equations the exact same way. We're going to look at this. We're going to subtract 4. We're going to get our 5x to the 3rd equals 135. We are going to divide by 5. And we get x to the 3rd power equals 27. And then to get rid of a 3rd root, we cube root. If we cube root the left side, we have to cube root the right side. That 3 gets rid of that. So we have x equals a cube root of 27. Some of these you're going to memorize. Cubed root of 27. 7 is 3 cubed. So that gets me to 3. Now, because we're taking roots, we should always remember to check our answer. So to come back, look at this and say 5 times 3 to the 3rd plus 4, does that equal 139? Well, That's 5 times 3 cubed is 27, plus 4 equals 139. And 5 times 27 is 135, plus 4 equals 139. And 135 plus 4 is 139, equals 139. Therefore, we know we justify that, yes, it is 3. Remember, anytime I'm taking an odd root, the third root, any odd number, if that number is positive, it's going to be a positive number coming out. But if that number underneath is negative, you can take odd roots of negatives. That would just be a negative out here. And remember, anytime this saddle number, this root is an even number, then if it's positive, it comes out positive. But if it's negative, that gives us the imaginary solutions that are not real. 3 more examples. We're done here. We're just going to be solving these equations again, knowledge of nth roots. So we're going to subtract our 1. We get 2x to the 4th equals 32. We got to divide by 2. We get x to the 4th equals 32 divided by 2 is 16. Now, because that's a 4th power up here, we are going to have to 4th root that to get rid of it. So x equals, and any time that root's an even number, remember you're solving an equation, there's both a positive and a negative root, potentially. The 4th root of 16, looking over here, is 2. So the answer should be plus or minus 2. But we're going to want to check our answers, thinking about it. 2 times 2 to the 4th plus 1, does that equal 33? Well, 2 to the 4th, we know, we said that's 16. This is 2 times 16 plus 1, 33. So this is 32 plus 1 to get 33. And yes, 33 equals 33. So the positive 2 is a solution. And now if I really look here, negative 2 to the 4th plus 1 equals 33. This is exactly the same because I'm raising a negative number to an even power. That's going to be 2 times 16 plus 1 to get 33. So I get my 32 plus 1, and I get 33 equals 33. So this one has 2 solutions. Remember, anytime even root, there are 2 solutions. But you need to check them, because sometimes they won't work. And then we're going to come over here. This one looks a little bit different. Now we have a fraction exponent, but we still need to get this 2 off, so we're going to divide by 2. So I get x to the 3/2 power equals 27. Half of 54 is 27. Now, because this is a 32 or a 3 over 2, what I'm going to do is I'm going to take that to a power of 2 over 3. I'm going to raise this side to a 2 over 3 because I know 3/2 times 2/3 gives me x to the 1st power, which is what I'm looking for. But the other side gives me 27 to the 2/3, and I got to remember how to deal with that exponent. Well, that's x equals, remember, fractions and the exponents are actually roots. Put the number underneath the root. The denominator goes in the saddle, and chuck the numerator of that fraction to the outside. So we're going to look, and we're going to say, oh, the 3rd root of 27. Well, if I look over here, that's going to give me 3. Then I got to square it. 3 squared, and that's a positive 3 because that's odd. Because that's a positive number, I will only get a positive root out. So that gives me 9. Because 3 squared is 9. I would plug that back in there, and I would check it to find out that, yes, we have solved that one correctly as well. I'm going to erase my board. One last problem. Final problem here, guys. 5 times x to the 2/3 power equals 45. We're going to solve this. We got to divide by 5 because we got to get our x all by itself. So I get x to the 2/3 equals 45 divided by 5. Yeah, 9. And then because this is a 2/3, I need that fraction up there to go away. So to get rid of a 2/3, I'm going to multiply it by the reciprocal of it. I'm going to raise that power to a new power, the reciprocal of the power, 3/2. And what you do to one side, you have to do to the other side. Because then that 3 cancels that 3, that 2 cancels that 2. We just have an x equals 9 to the 3/2 power. But then we need to look at this. Oh, there's a fraction over a number. So we want to see what is that root that we are looking at. The 9 goes underneath. The 2 comes here. We're going to chuck the 3 outside. What is the square root of 9 when I'm solving an equation? The square root of 9 is both positive and negative 3, and then I got to cube it, which means my answer is plus or minus 3 cubed, which is plus or minus 27. Should be my answer there, but you should definitely check your answer, which is 5. And now it's a cube root 27 squared. Does that equal 45? And because it's a cube root of 27, so that's 5 times 3 squared. Does that equal 45? Well, that's 5 times 9. Yes, it does. 45 equals 45. So I know my positive 3 works, and I should definitely check my negative 3, which is just coming right over here. 5. I'm going to take a cube root of negative 27, and then I got to square that. Does that equal 45? Well, there's my 5. The cube root of negative 27 is negative 3, but then I got to square it. I got to raise it to an even power. So I get 5 times negative 3 times negative 3 is 9, gives me 45. So I get another mathematically true statement, 45 equals 45. If either one of these would have not been equal, I would have thrown that solution out. But because they both worked, I keep them. Hopefully this makes a little bit of sense. I hate this. I want to go back to school. Everybody's saying the same thing. Never thought I'd hear it. Have a good night.